Hello all, let's learn about question number 38 from GATE Biotechnology 2021 paper. So the question is, which of the following nucleus or nuclei is or are NMR active? Option A, 1 hydrogen, which is a proton, protium, and option B, 13 carbon, option C, 16 oxygen, and option D, 32 sulfur. So NMR spectroscopy has become one of the most frequently used analytical tools to elucidate chemical structures. So it is particularly useful for carbon-based chemical compounds, which are known as organic compounds, the molecules that make up all living things and many substances that we interact with on a daily basis. So nuclear magnetic resonance is what the full form of NMR is, and it's used to determine the chemical and physical properties of organic compounds and inorganic as well, but mostly organic compounds. So yeah, the protons in the atoms of the molecules, they behave as magnets, and it repels and tries to rotate the other atoms present near it. So the NMR machine creates a magnetic field and directs this magnet, which are the protons, in whatever direction it is to the stable state. Here's a diagrammatic representation of the NMR spectrophotometer. The theory behind NMR comes from the spin of a nucleus, and it generates a magnetic field. So without an external applied magnetic field, the nucleus spins are in random directions, as you could see here. But when an external magnetic field B0, BO is present, the nuclei either align themselves with or against the external magnetic field. So many nuclei undergo magnetic resonance. In general, nuclei composed of an odd number of protons like 1H, the protium ion, and the isotopes of atoms like molecules like 14N, 19F, and 31P, or an odd number of neutrons like 13 carbon. All these show magnetic behavior and they're marked as active in this column. So if both the proton and neutron counts are even, like 12C or 16O, the nuclei are non-magnetic. So it is the positively charged nucleus that NMR spectroscopy detects and gives us a lot of information about the overall structure of the molecule. So different nuclei have different spins, and the ones with spin 1/2 can exist in one of the two possible spin states. So these include the following atomic isotopes. The hydrogen nucleus, usually referred to as proton, and present in most of the organic compounds, and is the most frequently analyzed by NMR. The precision frequency or the Larmor frequency is given by this equation and is dependent on the strength of the magnetic field and the gyromagnetic ratio, which is a constant for a given isotope. So if you apply a short radio frequency pulse or RF pulse at the right angles to B0, the nuclei will flip down to the XY plane in unison and continue to precess. So let's represent the average magnetic moment of a set of nuclei by the sphere. So at equilibrium, the magnetization vector will be aligned along B0 as depicted here. And we have seen that the RF pulse will flip the magnetization vector to the XY plane. So the rotating magnetization vector induces a current in a receiver coil. So this signal is detected and amplified. So we can see that the oscillating signal sweeps out a sine wave with decreasing magnitude as the nucleus realigns with the magnetic field B0. So this wave is called the free induction decay or FID. So if each proton sweeps out an FID at the same frequency, then each proton would look identical and we won't be able to learn anything from the structure of the molecule. So this is converted to Fourier transformed signals, which gives us peaks in the spectrum. Let's consider two protons in different parts of a molecule, and each will be exposed to a different magnetic field depending on the electron density distribution. So the electron creates its own magnetic field which opposes the applied magnetic field B0. And a proton with a high electron density around it experiences a lower magnetic field and therefore a lower frequency. And a proton in an electron poor environment has a higher frequency. So typically protons in an electron rich environment are referred to as shielded, and those in an electron poor environment are referred to as de-shielded. Aromatic rings such as benzene ring can induce their own magnetic fields which can further modify the magnetic field around the proton. So now if we pulse these with an RF pulse, we will get two signals in our FID, one oscillating at a high frequency and one oscillating at a low frequency. The FID is a representation of the wave in the time domain. The Fourier transformation mathematically converts this to the frequency domain, which allows for a visual representation in an NMR spectrum, with the shielded protons giving peaks at the right side and the de-shielded protons giving peaks on the left side. Here's a simple molecule with hydrogens in 5 different electronic environments. So each type of proton will experience a slightly different magnetic field strength and will precess at its own frequency, giving 5 overlapping signals in the FID. So after Fourier transformation, we will get a spectrum with 5 peaks, each peak representing a proton or a set of protons in a particular chemical environment. So with this spectrum in hand, we can start to deduce the chemical space around each proton. So we have seen that an isolated proton or a group of identical protons will give an NMR spectrum with a single peak known as a singlet. Sometimes you will also have protons that are close enough that their magnetic spin states interact. So this is known as spin-spin coupling. So in this case, the peaks do not appear as a singlet but rather appear as a split peak, as you can see here. So this is known as a doublet. For example, if a proton A has a neighbor proton B in a different electronic environment, proton A will be affected by its neighbor and proton B will either be aligned up or down. Thus, proton A will be a doublet. So likewise, proton B will be split by the proton A and it will be a doublet as well. And two neighboring protons will give a triplet and 3 neighboring protons will give a quartet. So you can even see quintets and septets, which are like 6, 7 peaks in some cases. So this spin-spin coupling can give us valuable information about the connectivity of atoms in a molecule because it shows us which protons are close neighbors to which protons. So the structural information, so what are the structural information from features of a hydrogen NMR spectrum? So we can get information about the position of signals. So it indicates what types of hydrogen the molecule contains, and the number of signals, which indicates the number of different types of hydrogen in a molecule, and intensity of signals indicates the relative amounts of each kind of hydrogen in the molecule, and spin-spin splitting of signals, it gives further information of the neighboring environment for various hydrogens in the molecule. So here's an example of the hydrogen NMR spectrum. So an NMR spectrum is a plot of the intensity of a peak against the chemical shift, which is measured in parts per million, ppm. Now what is a chemical shift? So the chemical shift of a carbon-hydrogen bond increases with increasing alkyl substitution or electronegative atoms attached. For example, here we could see that with increasing number of alkyl groups R1, R2, R3, the chemical shift value also increases. So the absorption of alkane hydrogens occur at a relatively high field. So hydrogens close to an electron withdrawing group like halogens or oxygen are shifted relatively lower field, which means that they are de-shielding. So the more electronegative the atom, the more the de-shielded methyl hydrogens are relative to methane. So here's a table with values for chemical shift for each group. So with the fluoride group, the chemical shift would be 4.26 of the CH3, and with iodine, it would be 2.16. In a magnetic field, the electrons of a carbon-carbon triple bond are induced to circulate. But in this case, the induced magnetic field opposes the applied magnetic field B0, like we already saw. So the proton thus feels a weaker magnetic field, so a lower frequency is needed for resonance. So the nucleus is shielded, and so the absorption is higher. So you don't have to remember like for which kind of molecules and which interactions what the value of the chemical shift is. So you already would have a standard table for that, which tells, like for example, for benzene attached with the hydrogen atom, the chemical shift would be something between 6.5 to 8. So yeah, you just have to look up those values, and based on the position of the peaks, you can identify which molecule is present, which atoms are present, and how they are arranged. So here's an example. Like we said, the benzene ring attached with hydrogen, it's highly de-shielded, and the chemical shift would be 6.5 to 8 parts per million. Whereas the C triple bond C attached to a hydrogen is shielded, and its chemical shift would be lower with 2.5 ppm. Now if you have a look at the carbon NMR spectrum, so these are easier to analyze than the hydrogen spectra because the signal splitting can be avoided, because carbons cannot be very close to each other, as close as like hydrogen. So H3 would be 3 hydrogens that are close to each other. So that would not be the case with carbon. So each type of carbon atoms appears as a single peak with one hydrogen decoupling. So let's now first look at a simple example of how to interpret the NMR spectrum. So to interpret the NMR spectrum, we need to use a method that will help us to systematically first understand the context, what do we already know about the molecule, and then how many different proton environments are there in the molecule. And for each proton environment, what can the chemical shift tell us, how many protons are there in the environment, and what are the splitting patterns tell us about the number of protons on adjacent carbons. So we start by looking at the context. What do we already know about the molecule? So in this case, the question would tell us that the molecule, it's an ester. We know this, and we also know that this is a proton NMR spectrum because the chemical shift scale, the scale on the x-axis, is from 1 to 0 to 11 parts per million. So in case of carbon 13 NMR spectrum, it would be up to like 200 ppm. Looking at how many clusters of peaks are there, that would tell us about how many proton environments are there. So here we could clearly see that there are 1, 2 and 3 proton environments which are labeled A, B and C. Now we need to have a look at the chemical shift for each of these environments. So peak A has a chemical shift of 3.7. If you look at the x-axis, it has 3.7 ppm. And if you look at the NMR data sheet, you'll see that an environment with 3.7 ppm is a proton, a hydrogen on a carbon connected to an oxygen atom. And then peak B is at 2.4 ppm. So that is a hydrogen on a carbon connected to a carbonyl group, that is C double bond O. And then finally peak C is a hydrogen connected to a carbon that's part of an alkyl group. Next, we need to use the area information. This is the area under each peak, and it tells us how many protons are in that environment. So these numbers are generated by the instrument. So it calculates the area under each peak and it gives us the number near each environment. So here for peak A, there are 3 identical hydrogens in the environment that makes a CH3 group next to an oxygen. And there are 2 protons in environment B. So there's a CH2 group near to the carbon, and there are 3 protons in environment C. So that is an alkyl methyl group. So we have got a list of all the fragments of our molecule. And now we just have to put together all these fragments. So this is where the splitting of the peak helps, because it tells us the sequence of the pieces. So peak A is a singlet, so there is no carbon connected to the carbon with the hydrogens for peak A that has a hydrogen on it. So no hydrogen on the adjacent carbon, and that fits with an oxygen being connected to that carbon. So peak B is a quartet that tells us there are 3 hydrogens on the carbon adjacent to this. So it's looking very much like the methyl group here is connected to the CH2 here, and it's confirmed because environment C is a triplet, which tells us that there are 2 hydrogens on the adjacent carbon, and that signature of a triplet and a quartet linked to each other is very characteristic of an ethyl group. So now we have all the information necessary to map out the structure of the molecule. So we have the methyl group, and then the oxygen, then the carbon, and then an ethyl group. So this is methyl propanoid, and we just label which protons are responsible for which environment in our molecule, and we can see that it's all consistent. So again, just looking at the structure, this CH3, this R group would be connected to a carbon with 2 hydrogen molecules. So you just flip this around. So this carbon is connected to this carbon CH2 and C double bond O, and this carbon is connected to this oxygen. So O, and we have this group over here. So this is how you read an NMR spectrum and identify what molecule the compound is. So now coming back to the question, which one of the following nucleus is or are NMR active? So like we saw, nuclei with odd number of protons, like the protium ion, and odd number of neutrons, like 13 carbon, they are NMR active. So option A and B are the correct answers for this question.